Yes, sir, I got it.
Yes. Process with some examples and techniques. The same operation can be done for our continuous time system and signals. The logic is same, okay? The logic was what? That the input of an LTI system can be expressed for the case of DT, for the case of DT system. If you signal is DT, then we can express signal as a weighted sum of impulses, then use superposition principle there to calculate the output for individual samples of your signal, then you sum them up, and that sum is the convolution sum. The same technique can be used for the case of continuous time signal. In this case, what you need to do, our assumption is our system is linear time invariant, and the input signal can be expressed as an weighted integral of impulses. Then the same principle can be used here just to calculate the output, and that output is actually, we call it zero state output. The assumption that we assume that before application of the signal, your system doesn't contain anything in it. So let me share the slide. Okay, then this is your convolution integral. Okay, it is there in your book. Now you can easily see that if we have an arbitrary signal, in our first few classes, when we expressed our signal with impulse function, we have shown that any signal xt can be expressed as a weighted integral of this form. This is very similar to your dt case, where your xn was expressed as weighted sum of over k xk delta n minus k. Can you remember it?
Sir.
Okay, this was for our DT case, and the corresponding case for your CT signal is this. So if we have our thing there, your logic is what? That means we are expressing our continuous signal into huge numbers of signals using impulse function, and those individual signal will give you the output. All those output can be summed together to find the total output of your system. So,
sir, a question I have. Sir, in the last class for the convolution, we saw that we are shifting the time shifting signal and multiplying with the x tau. Then we multiplying the individual magnitude and summing them. But sir, in correlation, like autocorrelation or cross correlation, we see that we also shift the time shifted version of the wave and multiply them and sum them. So what's the difference?
Okay, then
between
you just try to explore it, because at that time I cannot remember your correlation function. For this reason, I cannot address this question. Okay.
Yes, sir.
Okay, because if I have the thing with me, then I could have answered this thing. Okay, you can explore yourself. If there exists a similarity between them, they are similar, no problem. Okay. Then in our case, we are calculating the output of our system. Okay, in the case of correlation, you have your two signals there. Then if the similar, whenever we are multiplying these two signals, actually we are calculating the similarity between these two signals. Okay. So this mathematical approach can be explained in whichever cases we apply it. So if this coincides with your correlation, then you can find some relationship with that mathematical relationship with integral and your convolution integral and correlation integral. Okay. But in terms of system responses, when we have our system impulse response known, then we will use convolution to find the zero input state response of our system. And as this question is a bit specific, okay, I will explore it. Then you can communicate with me later so that I can discuss the thing with you. But in this case, we will not be discussing about correlation. let us start with what we have our system with. Now, this, you know, this thing from your basic thing, okay, that whenever you have a system, that system okay, takes an input, say xt, then it will take, give you an output yt, then that output yt is nothing but the system is performing some operation on x, then giving you the yt, okay. So this operation is very generic. So in this way, we will get an output. But mathematically, what will happen in order to derive the correlation, we can directly go to this integral. But as you have some introduction about your correlation earlier, convolution earlier, continuous time case for Laplace transform. But we want to refer it with respect to some system. Okay, that's why let us proceed with finding the response of our system using LTI concept. Now, for example, that we have an impulse there at the origin. If we have a signal, for example, say this is your signal, and if we multiply the signal with an impulse at the origin, what we have seen earlier, then what will happen? That is actually can be represented by what? Because it will pick the value of your signal at x equal to 0. So the value of your signal will be this, and this will be equal to delta. Your system is something like this. In earlier cases, it was a sequence of numbers, but in the continuous time case, it will be a continuous signal, okay, impulse response. That means if we give an input delta to our system, you will have the output there. That output will be your HT. Okay, this output is shown there. That HT is the impulse response of our system. Now, if your impulse is, for example, scaled by x0, then resultantly what will happen? Your output will be scaled by the same amount, isn't it?
Yes, sir.
Yes, sir.
So as a result, what you can do? Generally, you can do that. That next, you can shift your impulse, for example, at a certain location. Then you perform the same operation. Again, you shift your delta into another location. So that shipment in our discrete time signal was discrete, but in the continuous time signal, it will be continuous. In this way, if we have our impulse responses there, and those impulse responses can be added together, like your continuous discrete time case, to find the total output of our system. Okay, so this concept is similar to the concept that we used in our discrete time case, but here instead of sum, we will be using an integral, as our shipment will be what we call continuous rather than discrete. So your next slide shows the thing to you. Okay, I have taken the thing from BP Lathi's book. You can have a look there. But this is not that much difficult to be understood. You can easily find this. Okay, just whatever I discussed in the last slide, this is summarized here. Okay, we have an impulse at the origin, corresponding output is this. If we shift the impulse here, your output will also be shifted. If we scale the impulse at the location of the impulse by the signal amplitude, then your output will also be scaled by the same amplitude. If we keep going, for example, in shifting our impulses and try to find the impulse response and sum them together, then it will be taking in the form of a continuous output, YT, something like this. Okay, we will be illustrating this thing by using some example. Then you will find that those things are not very difficult, very simple. Okay, so this will give you an integral that is we call convolution integral. Okay, so let us proceed with the next. This is what the summary of the figure. Okay, here you see that your input is this, you are getting an output. Your system is LTI. Then what is happening? Your del t is giving you st. If we shift the del t, then your output will also be shifted by the same amount of time. Then if we scale the input with the value of our input at the location of impulse, then your output will also be scaled in the same way. Then if we keep going, changing the position of n, then we are traversing the whole time region of your signal. Then for each of your individual cases, we will have our output. Then we have to sum all the output together to get our yt. When, for example, this shipment delta tau is tending to 0, that means your sum will be become a continuous integral, and that continuous integral is this. Okay, this integral is called convolution integral. Probably you have seen this integral earlier for two functions. Okay, and we usually write this in the short form as xt convolution st. So this is your convolution integral. If we, like your discrete time case, here in this case, you have to know your st. Unless your st is available, this operation cannot be done. So we'll be discussing how to determine the impulse response. Okay. Meanwhile, in your control engineering, you have already defined your transfer function concept. So if we can find the transfer function, then the Laplace inverse of the transfer function of a system is the impulse response that we discussed in the last class. Okay. So in this way, you can do that. But in time domain, by using differential equation solution, you can also find the impulse response. Okay, we will discuss later how to find the impulse response of a continuous time system. Now, in order to evaluate that integral, this integral is to be evaluated in the same way that we perform the sum. Okay, can you identify how to do that? In your sum, in our discrete time cases, we were given, for example, xn, then we change the value of n to k, we determine xk, okay? That will not change the profile of your signal. Then your hk, hn was given, then from hn we determine hk. Then we reflected the hk. Then after reflection, we shifted the hk, then we perform the sum. Okay, these are the steps. Similar step will be followed here in this case. Okay, you see that your xt will be given. Your xt will be given. Then from your xt you change the variable tau. Then your x tau is there. Then your st will be given. From your st you determine your h tau by changing the variable. Then you reflect your h tau. Then you shift your h tau by t. Okay, depending on the sign of t. Either the shipment will be to the left or its shipment to the right. Okay. After having this thing shifted, then you multiply your x tau with ht minus tau. Then you integrate it between the time limit. Then that will give you the output of your signal. In this case, it is actually a sum hk xk into h n minus k. In this way, you can find or evaluate the integral. All these steps are described in your book. Okay, you can have a look. Now, okay, you can evaluate this integral in two different ways, either by using integral using analytic form, or can evaluate graphically. Okay, we will be showing, okay, by evaluation of using analytical method, you have already experienced it in your Laplace transform course, so we will not be discussing that much about it. Just I will be discussing more about your what you call graphical technique. Okay, the whole process of evaluation is that I described there is already there in 1 and 2. So and the whole procedure is there described. You can have a look. Okay, just from h tau to minus h tau, then shift it, then multiply it. Then we can define an intermediate function, the wt tau. That wt tau is the multiplication of these two functions. Okay, like our wnk for the case of discrete time signal. Okay, then we have to evaluate that integral. In order to just apply this thing in our real system, let us start with an example. Okay. Okay, consider this example. Okay, you have your two functions given there. Your impulse response is there, st, and your signal is there. Okay, we have to calculate what will be the output of your system. Okay, that then output of your system, your yt would be equal to simply xt convolution st. Okay,
Yes,
so
sir.
okay, then we have to evaluate the integral is over t x tau is t minus tau. Okay, now you see that your convolution integral is commutative type. That means you can exchange the position of x with t. Okay, you can swap these two position. Okay, that means your xt convolution st is equal to st convolution xt. Okay, some other properties of your convolution is there. Okay, we will discuss the thing later. Now your first thing is what? We have to change the value of t to tau, isn't it? So
Yes, sir.
if we change the value of t to tau, will it change the nature of your signal?
No, sir.
Okay, only your independent variable will change. Okay, let me illustrate it by using the whiteboard. Okay, then it will be very clear to you.
Yes, sir.
We remember the signal. We have our two pulses. One is your input, another is your impulse response. Okay.
Yes, sir.
Now, can you see this whiteboard?
Yes, sir.
Now let us draw this two figure again. Okay, your signal was st was equal to ut minus ut minus 2, isn't it? And your xt was equal to what? Ut minus 1 minus ut minus 3, isn't it? That means your st is a pulse, your st is something. This is your t, this is your st, okay? 0 to 2. This is your st. And your xt was, okay, this is a 1. It starts from 1 and go there to 3.
Yes, sir.
So this is your xt. This is your t. Now, what you need to do, you have to change your t to tau, isn't it? The changing t to tau, you erase your t here, you erase your t here, you erase your t here, you erase your t there, okay? Then you put, for example, tau there. Okay, this is your h tau. Then this will be tau. This is your x tau. This will be tau. Okay, is that clear?
Yes, sir.
Next step is what? We have to reflect this, isn't it? If we reflect it, where it will go? Okay, it will simply 2 will go to minus 2 and 1 will be going there minus 1. Okay, so this is your minus tau, isn't it?
Yes, sir.
Okay. Then we have to shift it, okay? I am drawing the figure in a different color beneath your x, or even we can draw it over x just to see how your things are overlapping, okay?
Yes, sir.
Okay, let us draw the thing first here beneath this figure, okay, for your understanding. Hmm? Okay. It is minus 2. This is minus 1, okay? Now your pulse is this. This is your h minus tau. Okay, now consider that, okay, if we shift this pulse, we can shift in either way. We can shift to the left from the present position, or we can shift to the right from the present position. Is there any meaning of shifting this pulse into the left? Is there any meaning
No,
of,
sir.
no, because if we go in the left direction, we are going away from our original signal. There is no any chance of overlap. Then this movement is not there, okay? Then how to, in which direction we move then? We have to move towards right. If we move towards right, okay, then your time will be positive. Then in this case, what will happen? Consider that a general time t that we are moving. So we now draw our figure over our pulse just to show. Then you zero of your pulse, this color will go there at t, and the trailing edge can be there. For example, depending on the magnitude, it can be there at this location -2 plus t, isn't it?
Yes, sir.
Let me erase this figure then. Okay, I am now erasing it so that you can have a look. Okay, I am just rewriting the thing. So this location will be equal to the trailing edge of your pulse will be 2 plus this tab is sometimes creating problem because I am putting pen in one place, it is going other. It will be equal to 2 plus t. Is it okay?
Yes, sir.
Okay, now where is the overlap region? This region is your overlap, isn't it?
Yes, sir.
Fine. Now, can you tell me if you t, for example, if you, okay, let us put the result in this section. If your t is, for example, you're less than 1, will there be any overlap?
No, sir.
No, sir.
Because at t equal to 1, or the leading edge of your pulse just coincide with the trailing edge of your signal, isn't? Oh, yeah. So if you then you this portion hash portion is actually this portion is nothing. This portion is the product of x tau into h t minus tau. You can call it from your notation that this is your omega wt tau, isn't it?
Yes, sir.
Yes, sir.
Now, if we want to integrate, for example, this thing, we have to integrate our x tau is t minus tau, equivalently wt tau. Then what will be the lower limit of your integration?
1, sir.
1, and upper limit?
T.
T.
Upper limit t, okay? Is that clear? The reason is that you have to integrate over this, over the time where your overlap exists. So this is what, and your t is variable. If you just change the location of t, the value of this integral will change. Then that is equal to what? We know that within that region, your signal x tau has a magnitude equal to 1. And your h tau has also the same magnitude, okay? It can be 1 or it can be other than 1, whatever it may be, as this is your pulse, your signal is constant within that region. But if we have other functions, we have to write the thing accordingly, okay? In this simple case, it will be simply 1 multiplied by 1 into t tau. And this is equal to what? It is equal to t minus 1, isn't it? T minus 1, and that is valid
Yes,
for,
sir.
so yt would be equal to 0 in this region. Then your yt would be equal to t minus 1. Can you tell me from where to where this is valid?
From 1 to T.
1 to 3.
That will be valid. Okay, that will be valid. Your t will be valid from 1 to 3, okay? So it will be between these two limit. Now, if at 3, as the duration of your signal and the impulse response are same, then you see that that overlap, you see it is increasing. Is it not increasing? If you want to plot this figure, what will happen? Up to 1, no output is there. This is your yt. Up to 1, you have no output. Then your output is gradually increasing and reaching at a value equal to what? reach, say this is your time 3, then reaching at a value equal to what? Is it not 2?
Yes, sir.
This is reaching at a value of 2, okay? Now, when it is at 3, a complete overlap is there, isn't it? When your time is increasing, then your signal is going in this way, in this way, in this way, isn't it? So gradually that overlap region is increasing linearly, that is there in this figure. Now, when your time is going past 3, then what happen?
It will be 0 again.
Then what will happen?
0
So your pulse is now here, okay? That red position is now the position of your pulse, okay? This is your T, and that trailing is your -2 plus T. That means your pulse is going past, H is going past your signal, then your overlap region is this hash region, isn't it?
Yes, sir. It is decreasing.
Then what will happen? Again, after 3, it will begin to decrease. Okay, how to now find that integral? Now your integral will be again same x tau into ast minus tau d tau. But now the limit will be from where to where?
Sir, 3 to infinity.
You consider because this integral will have non-zero value only in this overlap region, isn't it?
Yes,
So
sir.
what is the overlap time spread of your overlap region? It starts at -t by 2, -2 plus t, and it ends at 3,
Yes, sir.
isn't it?
Yes, sir.
Because if you are going past 3, for example, your pulse is moving in this way. If your t is greater than 3, then what will happen?
It will be 0.
Okay, that your red pulse will be slipping, for example, your green pulse. No overlap will be there, okay? Then what is the value of this integral? Because this is 1, this is also 1. So your integral value would be equal to 3 minus -2 plus t is equal to what? Minus t plus 5, isn't it?
Yes, sir.
Yes, sir.
So your output would be equal to minus t plus 5, and this is valid for where to where? Because this will be valid from where to where? When your trailing edge of your pulse will coincide with 3, isn't it?
Yes, sir.
So that ultimate limit of this thing will be equal to what? -2 plus t is equal to 3. That means t equal to 5. So this is valid for 3 to 5, okay? Then again it will be 0 if your t is greater than 5. Is that clear?
Yes, sir.
Okay, can you plot this
Sir,
figure?
how are we taking the lower limit here?
Can anyone answer this question?
Yes, sir. The trailing limit of the HT is now passing through from the limit 1
You
to
see that, okay,
2 plus
okay,
t.
because you see that your impulse, shifted impulse has this trailing point, and this is your leading point, isn't it? So when it is going to the red position, then your t is coming here, and -2 plus t is coming in this position, isn't it?
Yes, sir.
Then from where to where you have to integrate? Over the overlap region, isn't it? Your overlap region starts at time t -2 plus t, this point, and that point is 3, because if you do not have any overlap in this region. Thus your integration lower limit will be -2 plus 3, upper limit will be
3.
3. Is that clear?
Yes, sir.
Then you have to draw this line, okay, at t equal to 3, because the result will show you that whether integration is correct or not. Okay, your output should be continuous. So you put your t equal to 3 in this equation, you will see that your output will be equal to 2. Okay, then it coincides with this thing at 5, output equal to what?
0.
So this is what your output. Okay. Now, if we can extend, for example, this problem in this way, okay? Consider that now we are increasing, for example, the duration of our signal. What will happen? Okay, let us consider that our impulse response is same. but our signal is impulse response is same. Now our signal is this, okay? Our signal is say start from 1 and it ends at say 4. Your signal is something like this, okay? This is 2, this is 3. Can you identify how will be what will be our output? Okay, up to, for example, 3, your what will happen when your signal is coming here, as you know that your impulse has the duration equal to 2, then what will happen? A complete overlap will be there, isn't it?
Yes, sir.
And at this location, your output is gradually increasing from 0 to 2.
Yes, sir. Then it will level.
Okay, then 3. Now you see that, and if you are going, for example, past 3, what will happen?
It will be the same.
Okay, then that amplitude, because the overlap region is remaining same, isn't it?
Yes, sir.
Okay, how can you prove it? You can easily draw a figure, because this is very simple geometry. Okay, if your time is now there and you are here, for example, okay, your time is, for example, say minus 2 plus t, this is your t. If your t is between 3 to 4, still your complete overlap will exist, isn't it?
Yes, sir.
So your complete overlap will exist up to what?
Up to 4.
Up to t equal to 4. Okay, your complete overlap will exist from up to t equal to 4. So your output is this. Then if you are going t is greater than 4, but it is less than 6, then what will happen? Again, a similar thing will be appearing, and
Yes,
your output, when it will go past your signal, okay,
Yes,
when
sir.
t plus 2 equal to 4, okay, that means your t equal to 6, okay. So for t is greater than 6, your output will be 0. So this point will be 6, then your output will be something like this, okay.
Yes, sir.
That flat region is coming from the fact that complete overlap is being maintained for a certain time, okay. Then after that, when your signal is going past, your impulse response is going past your signal, then again your output will be gradually decreasing, and when it is completely leaving, then output will be equal to 0. So in this way, figuratively, you can determine what we call
The output.
output of the system, okay. So this is actually this is the mixture of, without drawing this figure, you can also evaluate that integral. So my advice is, do you have your Alexander Sadiku's book with you?
Yes,
Yes,
sir.
sir.
Electrical circuit.
Yes, sir.
Is this book with you? Then I cannot remember which chapter it is. You go to Laplace transform, okay? Probably it is in chapter 14, or I cannot remember, okay? In the last cases, because Fourier transform and Laplace transform, they are in consecutive chapters, okay? Then, okay, in the elementary part of Laplace transform, you will find some exhaustive examples are there related to evaluation of convolution, okay? For the continuous time signal, not for discrete time. You can have a look there, okay? Very nice examples are there. I hope everybody will understand it, because the logic that we developed here is same logic is applied there, okay? It's very simple.
Yes, sir.
Okay, now an example is there regarding a physical something, okay? Before going to that example, let me talk about something, okay? For example, say, because if you do not have your physical reasoning with you, then you will never be able to, for example, interpret the result that you are obtaining from convolution, okay? I have discussed this thing earlier, that this is an RC circuit, a simple first order circuit, okay? And if you want to find the output YT at this location, didn't we discuss about impulse response in the last class?
Yes, sir.
Okay. Then the impulse response of this circuit ST was equal to 1 divided by RC e to the power minus T by RC, and you have to put UT there because otherwise it will become undefined. Okay, isn't something like this? Okay, if you want to plot it, consider that your R is equal to 1 ohm, C equal to 1 farad. Then what will happen? Impulse response would be equal to e to the power minus T UT, isn't it?
Yes, sir.
For these values of your R and C. Can you plot it? We can easily plot it, that your plot will be something like this, okay, HT. Okay, we are assuming that because in determining HT, we assume that your capacitor is not containing any charge in it, okay. Now consider that when our XT is now UT, okay, we have to find the output YT. What will be the YT? YT is equal to 1. You understand my question?
Yes, sir.
Okay, that is something like this. We call it unit step response of a system. Unit step response. This is your impulse response. When our input was equal to delta T. Now, if we have our unit step as an input, the corresponding output is called unit step response. Okay, this unit step response, YT. Okay, if you want to find if someone will tell you that find the unit step, actually unit step response appears to be like a DC signal, but it is not exactly equal to DC. The reason is that it has a discontinuity at time t equal to 0, isn't it? What is the difference between a DC and a unit step?
Sir, step starts from 0.
Okay, because yes, step, you see that if you want to draw the figure, this is your DC, okay? But your unit step will start from this location. Your unit step is something like this, isn't it?
Yes,
Yes,
sir.
sir.
So your blue overlay is actually, green overlay is what? This is your unit step, but this curve is your DC. So this is the difference between a DC and a unit step. But if we, for example, forget this region, then if someone is looking the behavior of your circuit or system in this region, far away from your time t equal to 0, it appears to be DC. The DC, isn't it?
Yes, sir.
Yes,
But at time t equal to 0 or near 0, these two things are completely different. So in this way, what you can consider from your basic idea, that you are applying a voltage across your capacitor at time t equal to 0, and that has an amplitude equal to 1 volt. Then how your output will be looking like? Because you know from your very basic thing from first year that your output YT will have, for example, this nature. Okay, your capacitor is gradually getting charged, and at a maximum value equal to 1 volt, isn't it?
Yes,
sir.
sir.
Okay, now let us start finding the response. For example, that this example is that, for example, the response is correct by using convolution. You have your two signals ST and AT given. Okay, now. So in order to find YT in this particular physical example, you have to evaluate the integral ST dot plus in convolution ST, isn't it? Now you see that convolution can again be evaluated in this way, because this commutative operation is possible for convolution integral. Okay, you can interchange the position of A center. Now, why we are doing this? Because of this property, sometimes it will be easier for you to evaluate or understand the thing graphically. The reason is that, okay, you know that HT has certain time dependency, and your XT will have certain time dependency and space amplitude. The reason is that if we have a signal with amplitude equal to 1 or constant value, okay, that reflection and what you call reflection and translation will not change, for example, the amplitude of your signal. But if we have a signal, that signal has some time dependency, something like this, say this is ut, then what will happen if we reflect this signal, if this time will also change, okay? But if we have, if we reflect it, then what will happen, unit step will go in this region, isn't it? But that amplitude will not change. But in this case, you see that if it is reflected, the reflected version will go there. So you have to write this e to the power t, and that t must be negative. Otherwise, your equation will be incorrect, isn't it?
Yes, sir.
So which thing you have to then practice? Okay, when reflection and translation is involved, you start with lower order, for example, time dependency signal. Okay, it can be your ST or it can be your XT. In our case, in the order of, for example, you see that our XT has a constant amplitude. So it is better that we reflect it and shift it. That means we evaluate that integral. Okay, it will be giving you the same result. And you see that, interestingly, you will see that without evaluation, you can easily obtain this figure. Okay, let me show it. So let me draw the figure, then we will be going to the equation. Okay, fine. So we have, I am not writing now, I am directly expressing x tau and h tau. So this is your tau, h tau. And your h tau is this. We are reflecting, for example, our x tau. So this is your x minus tau. Is that clear?
Yes, sir.
Okay. Now next thing is what you have to shift. For example, you have to obtain xt minus tau, because we are evaluating this convolution st, a convolution xt, and that is equal to integral over t h tau xt minus tau, okay, d tau, and that is also equal to integration over t h tau xt minus tau. Okay, you can go either ways. So in our first example, we followed this. You can also follow this in this example, and you can also follow this. Okay, in either ways you can go. Okay, now tell me, if your t is less than 0, will there be an overlap?
No, sir.
Then your overlap starts at what point?
T equal to 0.
T equal to 0, overlap starts. Okay. Now let us consider that our t is greater than 1. If your t is greater than or equal to 1, will that overlap will cease? Because although we have drawn this signal, it depends on e to the power minus t, something like this. Theoretically, that signal is this is tau. Okay. So theoretically, your signal is existing for tau t equal to 0 to infinity, isn't it?
Yes, sir.
Isn't it? At infinity, the h tau would be equal to 0. So, but it will be progressively decreasing for higher values of tau. But theoretically, that signal is existing from 0 to tau. So, if we, for example, shift the second curve, that is our reflected version of our input, reflected version of our input, reflected version of our input, say we are shifting our reflected version of the input. This is our the new position, this is your t. Then what will happen? If you overlap the figure here, then you will see that an overlap is there, okay, between 0 to t, isn't it?
Yes, sir.
Yes, sir.
Okay. Then that overlap will be continuing for t is greater than equal to 1. Okay. At 1, it will, no, t is greater than equal to 0, not 1. Okay. At t equal to 0, your overlap begins and it will be continued for other values of t towards infinity, isn't it?
Yes, sir.
Okay,
Yes, sir.
but gradually what will happen? The overlap area will be decreasing. The reason is that as you signal a star is decreasing as a rate of e to the power minus t. So if you want to evaluate the integral, your integral will be equal to what? From 0 to t, your a star is equal to e to the power minus tau, and your x tau value is equal to 1, and you have to integrate it to tau, isn't it? Is that clear?
Yes, sir.
Then what is the value? This is equal to minus e to the power minus tau from tau equal to 0 to t. So this is simply equal to 1 minus e to the power minus t, and you have to put ut there because no value is there in less than 0. Is it not the result?
Yes, sir.
Yes, sir.
Okay, are you seeing this thing for the first time? Because you have already know that if we apply a DC voltage across the capacitor, your capacitor VCT voltage is simply equal to magnitude E0 into 1 minus e to the power minus t divided by RC, isn't it?
Yes, sir.
Yes, sir.
It is going, for example, ut must be there because we applied our E at time t equal to 0. So other than your signal, with unit step, if you have a magnitude E0, then that equation can be generalized in this way. So you can easily identify that this, if you want to plot this, can you plot this?
Yes, sir.
Is it not something like this?
Yes, sir.
Yes, sir.
So that actually coincides with our earlier intuitive finding. So in this way, you can apply, for example, you what we call convolution to find the zero state response of any electrical system, that is LTI and linear. Now the case is what? Okay, one important issue is that if your capacitor is containing some initial value, then this convolution will give you only one part of your response, okay? Then for your initial value, you have to calculate your response separately, okay? We will be dealing this thing later when we discuss more, for example, the complete response of our system in more detail. Now, okay, at this point, the convolution operation is applicable for zero state response. That means your system is relaxed. Nothing is there in your system before the application of the input. Okay, this problem can be extended for a case that if we apply a pulse there, for example, instead of a continuous, what you call, instead of a unit step, if we apply a pulse there in your input, consider that this is your pulse, okay? Your pulse is something like this. Your duration is 0 to say 3. This is your xt. Then how your output will look like? Can you, for this RC circuit?
So it will increase and then slowly decrease.
That means if we plot it, it will, okay, say this point is 3. Consider this dotted line is the amplitude of your original signal. Then your capacitor output will begin to gradually charge, increase. It can go there, again can be there. Again, at this point, it is begin to discharge, isn't it?
Yes, sir.
So this phase, okay, now your curve can go, for example, your curve can go in this way, or it can go in this way, or it can even go in this way. It depends on what value. It depends on the RC value, okay? That value is called time constant. You know about it.
Yes, sir.
So if you have a larger time constant, it will take longer time to charged. If you have a shorter time constant, it will be quickly charged, okay? For this reason, in many of our electric, because this concept is very important in laboratory also, okay? If you have an oscilloscope, have you ever used oscilloscope?
Yes, sir.
Then what particular thing you have to know before starting to use oscilloscope?
Sir, the ground.
Only ground.
Sir,
Okay, in your oscilloscope, there exists some input point. We call it the location of probe. For example, say we have a 2-channel oscilloscope, something like this. 2 probes are there. Some informations are retained in the front panel of your oscilloscope here, just beneath the input point. Have you ever seen what are the information there? What are the thing written there?
yes, sir.
Can you tell me?
Sir, maximum voltage or current that it can measure.
Okay, this answer I am not satisfied. You got my point. This can be one of the what you call issues, but many other issues are there that is very mandatory to learn in order to use an oscilloscope effectively. Try to learn it. What are the important information that we need to use there? Okay, when we use, for example, a connector there to connect, we use a quantity, we use it where we call it probe, and it has a definite shape. It is also a 2-wire conductor, but not, okay, can you replace that probe by using a simple 2-wire conductor? For example, this probe has some feature, okay? But without that probe, if we replace it by a 2-wire conductor, something like this, okay? This is one. We are connecting one to this point, connecting another to this point, and this will go to your signal. Can you use it?
Yes, sir.
Yes, sir. Okay, you are going to be 4th year student after a few days. Try to find the answer, okay?
Yes.
Then people will not use probe because it will cost 10 taka, and probe may cost sometimes 10,000 taka.
Yes, sir.
Why we need then probe if your wire is enough to measure your signal? So you want to learn your experiment physically, but these are the fundamental things that I could not find, for example, any viable answer from any student when I ask them in the classroom. So try to learn it.
Yes, sir.
Because we have because many students are playing with what we call oscilloscope. Okay, they are simply turning the knob, and when a signal is appearing, they are very happy, but they do not know how your signal is appearing. So your RC value is one of the important factors of your input side and your probe side, just to understand to effectively use a probe to measure signal by using an oscilloscope. The reason is that if your RC is very longer and your pulse is very shorter, okay, then what will happen? Before getting your system charged, your pulse can disappear. So you will see nothing. For this reason, each oscilloscope has a certain upper range of frequencies. Beyond this, you cannot use that oscilloscope. So we have 2 types of oscilloscope. One is analog, another is digital. In the digital case, a data rate is to be mentioned there, the maximum data rate that your digital oscilloscope can handle. Similarly, in the analog oscilloscope, you will have the frequency limit in terms of megahertz. That up to that hertz, you can use your oscilloscope. Beyond that, you cannot measure it. So this is your case. Now, can we evaluate that thing case by using the same convolution?
Yes, sir.
Okay. Then in this case, what will happen? What modification will be needed? In this case, what you want to do, you can do, you just truncate it, okay? You pause now this, okay? This is your T, and that would be equal to minus T plus 3, okay? If it is minus T plus 3, you see that when you are here at, okay, when this trailing edge, for example, will coincide with 0, when this edge of the pulse will be coinciding with it,
When t equal to
when
3.
T plus 3 equal to 0, that means T equal to 3, okay? So at t equal to 3, it is coinciding. A complete overlap will be existing, isn't it?
Yes, sir.
Yes.
So when we'll be plotting, then gradually increasing, going to, for example, this point, a complete overlap is occurring at 3. Then when we are going past 3, then what will happen? Again, complete overlap will be there, but your signal will be decreasing. But in our earlier case, we integrated the signal from where to where? From 0 to t. But in this case, when complete overlap will be occurring, then when from where to where you have to, okay, that means if your t is greater than 3, then from where to where you need to integrate?
Sir,
Because from t is greater than 3, your pulse will be going here, okay? This is your minus 3 plus t, this is your t. Your integration will be from minus 3 plus t to t, isn't it?
yes, sir.
That's why you complete the rest of the thing by your own, okay? And you see that and plot it. And you see that your output will be looking like this, okay?
Sir, at first we were taking a unit step input, but after that you have just truncate one portion and make it a pulse. So isn't it different from that thing?
Don't you think that it is same? Do you think that these two are same?
Sir, up to a certain portion it is same, but if I continue the pulse, it will...
That portion is same.
Yes, sir.
But this portion is not same. It is very common sense that your capacitor is charging up to that point, then you do not have any input there. Now in your system, what will happen?
It
Your
will
input
just
is
decrease
0.
the charge.
Then it will be decreasing, discharging in this way.
Yes, sir.
So are these two things are same. So
Sir,
up to this point, okay, your unit step concept and this concept is same. And this will be valid for time t equal to 0 to 3. When you are going time t is greater than 3, then this is what this concept, okay?
yes, sir. That 3 you take, is it random or in
What do you mean by random?
the pulse, the
What?
length of the pulse?
Length of the pulse depends on your real system, okay? There is no any randomness here, okay? We consider that duration is 3, but another can consider that duration is 4, that 5. It is up to you, just to illustrate, okay? You see that sometimes you can apply this type of signal in your system, okay? A square pulse, okay? Something like this. Can you extend this thing there?
Yes, sir. We can.
Okay, then you extend it. Okay, you see that your signal is going there and again you are discharging, okay? Then again it will begin to charge, again going to discharge, okay? So your output will be looking like this. But by using simple convolution, you cannot do that. The reason is that when you are starting this second phase, okay, your signal can, your capacitor can have your RC values so that it will be discharging slowly and going there rather than going to 0. Then this value is coming from your previous input, not from that input. So at this time, this value will be acting as the initial value for this portion of your pulse, okay? In order to incorporate this in your equation, you need to solve the differential equation, okay? We will discuss that thing later. But now, as we are not considering the initial values, okay? Our convolution operation will be valid for this portion only. If we use convolution for this system, that after having the convolution done, you have to add the contribution of this initial value separately. Otherwise, your equation will not be correct. We will discuss the thing later when we will be considering the complete response of our system. So there is no any randomness here, okay? Nothing random. All the thing that we are considering are deterministic, and the duration of your pulse is your choice, just to illustrate the process, okay? This is not a real system. It is a fictitious system. We just
Yes, sir.
considering just to illustrate what we call
Example purpose.
just for example purpose. That's it.
Yes, sir.
Now, okay, because you see that although we are using graphical thing just to illustrate the integral, but without using your graph, you can also evaluate mathematically if the equations for mathematics, equations for your h and x are available. Now, what is left there then? Okay, we have illustrated this thing. Then all the results are there, and the RC circuit is there. Okay, here you see that your pulse duration is how many seconds?
2 seconds.
2 seconds. Okay, your impulse response is minus 2 UT. Okay, so accordingly, even it can be 1 second, it can be less than 1 second. It depends on in which example you are following. Okay, you can explore by changing the duration of your input pulse. Okay, even you can write few lines of your MATLAB program to evaluate that integral. Okay.
Yes,
The
sir.
thing that I have discussed earlier is also illustrated in this problem. What is the difference of this technique and the technique we followed? Okay, can you see it?
Yes, sir. We can see the slide.
Okay, you can see the slide. Now you see that here in this case they reflected H rather than X, isn't it?
Yes, sir.
Yes, sir.
Okay, then you follow this example and you see that eventually the same result will be obtained. Okay, in this case, you see that when you shift the thing, then you have to consider, okay, now consider that if we shift the thing in this way, that your HT is, your H tau is e to the power minus tau, isn't it? If we shift it to h minus tau, it will be equal to e to the power tau, okay? But time is shifted. Now, your signal is something like this, okay? Now, in this case, if we want to replace, for example, our tau t to, for example, if we want mathematically, we have our h tau. We want to obtain h t minus tau. Then what will happen? We have to replace our t by t minus tau, isn't it?
Yes, sir.
Yes, sir.
Then initially that equation was e to the power minus t. Then this equation will be then what? E to the power t minus tau. Okay, so you replace your equation. The equation of this portion will be equal to, this portion will be equal to e to the power t minus tau. And then you evaluate it. Actually, mathematically, changing the independent variable will be reflected in both parts of your equation, isn't it? You have to replace your t by t minus tau.
Tau.
And I hope the rest of the process is described in the next slide, or if not, you can look at your book, okay? Right? This is described here, okay? So in this way, you can easily proceed with calculation and try to validate it with our earlier assertion. So with this thing, okay, let me discuss some properties of our LTI system. You see that your LTI system can have a single system, very simple, but it can have multiple, what do you call, subsystem connected either parallelly or in cascade manner. Okay, so two examples are there. One is your parallel architecture, another is cascaded one. Okay,
Yes, sir.
not cascaded one actually. Another, this representation is the equivalent representation of this thing. Okay, it is not cascaded. Now you tell me, we have two systems. One is H1, another is H2. Impulse response of these two systems are given, H1T and H2T. We are feeding same input to both systems and collecting the output and summing them together to get the total output. Okay, so this system output can be thought as say Y1T. Their system output is Y2T. Okay.
Yes,
Then
sir.
your total output Y2 would be equal to Y1T plus Y2T. Fine. Then your Y1T equal to what? Your Y1T can be written as XT convolution H1T, isn't it?
Yes, sir.
and your y2t is equal to
xt convolution
x2 convolution
h2t.
then your y1t, you sum them together, and by using a simple thing, you can group them together. You will find, for example, an equation something like this. Okay. So the resultantly, what you are obtaining then, that means we can obtain a system something like this. Then the total impulse response of the system will be equal to sum of the impulse responses of your individual system connected parallelly. Okay. This property is distributive property of your convolution integral.
Yes, sir.
And this is also related to linearity and superposition. Okay, this you can think that the output is the superposition of your two individual subsystems. Okay, the next property. Okay, this illustration is for your DT case. You try to look at it. The same property will be applicable for DT case. Okay, this is your distributive case. Okay, you see that in this case, your one output of your system is fed to the another system. Okay, if we go in this way, and if we calculate the output, you will see that your total output of your system will have something like this. Okay, that means, okay, you can see that. Okay, let me write. Okay, you try to look at your mathematics, but I will be showing this thing very intuitively. Okay, you consider this thing, that your okay, your ZT equal to what? ZT, that means intermediate output equal to
xt convolution h1t.
ST convolution H1T. Then your YT equal to your
zt convolution h2t.
ZT convolution H2T. Okay. Then if we replace our Z2T, then it will be we are having this thing. Okay. You can easily group this thing together. That we can write that XT convolution with a group equal to H1T convolution H2T. Okay. That means you can obtain a system. That means you can now tell that we have our combined, for example, impulse response. That impulse response is equal to H1T convolution H2T. So if we want to conclude the thing, then what is happening in essence, that if we have a parallel system, then your combined, for example, total HT would be equal to sum of your HTs, isn't it? Sum of your HTs. But if we have a cascaded system, your H1T would be equal to convolution of all the systems, impulse response of your system involved in the system. Okay, this is for your two subsystem. But if we have multiple subsystem systems are in this way, then that convolution operation might contain some other term. So this is what from my part today. You can stop recording. We'll give you a presentation. Your class test will be on the 14th using IUT LMS from 2 to 2:30.
Yes, sir. Chapter 1.
Yeah, I have already probably mentioned this thing to you earlier. You can stop your recording.